Okay, average cost, revenue, and profit. So we're going to let capital C of X be the total cost of producing X items. If that's the case, then the average cost per item of producing X items is given by C of X over X. And it might be easier to understand if we put some numbers on it. So let's say, for example, that you're the producer. Say you produce 10 items. Keep it simple for the moment. And it costs, let's say, $200 total to produce those 10 items. So then the average, what we're talking about is the average cost per item. It's your total cost divided by the number of items you produce. So if you produce 10 items and it costs you $200 total, your average cost per item would be $200 divided by your 10 items. So it would be $20 per item. Okay, that's total cost divided by the number of items that you produce. Okay, if R of X is capital R is the total revenue from the sale of X items, then the average revenue per item from the sale of X items would be capital R divided by X. It's your total revenue divided by the number of items that you sold. And similarly with profit, if capital P of X is the total profit from the sale of X items, then the average profit per item from the sale of X items is capital P of X divided by X. Okay, we're going to look at multiple graphs and quantities and look at how they change, and then we're going to find the rate of change of the average cost per item. Okay, so generally speaking, as a company produces and sells more and more items, so as X increases, total cost and total revenue are also going to increase most of the time, unless you have some weird circumstance. Total profit's also going to change as more items are produced and sold, but it's harder to say whether profit's going to increase or decrease as you produce and sell more items. Okay, so let's start by analyzing cost here, average cost per item. So suppose a local church finds that the cost in dollars of producing X t-shirts can be modeled by C of X equals 140 plus 13 times the square root of X. So we're going to sketch a graph of C of X. Actually, we're just going to use a calculator to look at the graph of C of X, the total cost of producing X t-shirts, and look at, in particular, how does the total cost change as more shirts are produced. Here's the graph of C of X, total cost equals 140 plus 13 times the square root of X. So it starts, its y-intercept is actually, zoom in a little, it's actually at 140. You can't quite tell, I'm not zoomed in enough, but it does start at 140 because that's the fixed cost. When X is 0, it still costs you 140 when X is 0. So your cost of setting up shop. Then the first t-shirt, let's see, if X was 1, the square root of 1 is 1. So your first shirt would cost $140 plus 13, or $153. But then as X gets bigger and bigger, each shirt does not cost an additional $13. It gets cheaper and cheaper to produce more and more shirts. So each shirt costs a little bit less than the previous shirt for total cost, because you've already set up your shop, you've already got things going, you're already moving, right? So that's that graph. Let's go back over here. Okay, so we can just do a quick sketch here. So it starts at 140 and then it goes up like that. So how does the total cost change as more shirts are produced? Well, it looks from this, because it's increasing, and this is a graph of total cost. Maybe I should label that. This is a graph of total cost C of X. So total cost increases, but more and more slowly as more shirts are produced. So what do you think will happen to the average cost per item as more t-shirts are produced? Okay, so because total cost increases but at a slower and slower rate as X increases as we produce more shirts, the average cost per shirt should decrease. As more shirts are produced, it should cost less and less for each additional shirt. Okay, so the average cost per shirt should decrease as we produce more shirts. So sketch a graph of the average cost per t-shirt from the production of X t-shirts. So what we're now going to look at the graph of is C of X divided by X. Okay, this is the graph, if you look right here, of C of X divided by X. So it starts out, it's actually got an asymptote at 0. And then as you produce more and more shirts, so as X increases, we can zoom in a little bit more here even, the average cost per shirt decreases, okay? And it starts getting to where the average cost per shirt gets quite low, actually, out here. So let's sketch a quick graph of that. So the average cost per shirt decreases a lot, and it's probably got a horizontal asymptote there. Okay, I'm just going to sketch it like that. So as more shirts are produced, how does the average cost per t-shirt change? Well, it does decrease as we predicted. It decreases, and let's look at what it approaches. So the average cost per shirt, let's write it out. Right here, C of X, which is 140 plus the square root of, why did I write it out like that? That's funny. 140 plus 13 times the square root of X all over X. Okay, so as you can see, as this goes out, there is a horizontal asymptote there. It's not going to approach 0. The average cost per shirt is never going to approach 0, but it's going to get pretty small. So you guys know how to find horizontal asymptotes. You actually take the limit as X goes to infinity of this 140 plus 13 root X all over X. The highest power of X is actually X to the first right here. So this would be, let's see, that's an X to the 1/2. So I'm going to multiply it by 1 over X over 1 over X. Actually, I was completely wrong. It is going to approach 0. So when we distribute this out, you may be able to see that now too. We're going to get limit X approaches infinity of 140 over X plus, let's see, this is 13 root X divided by X simplifies to 13 over the square root of X all over 1. Now both of those approach 0. This one approaches 0 really slowly as X goes to infinity, but they do approach 0. So this whole thing approaches 0 over 1 or 0. So I guess its average cost, it does make sense, per shirt eventually approaches 0, although because we have a square root in that denominator, it's going to take it a long time for the average cost per shirt to get incredibly close to 0. So you'd have to make a lot of shirts, in other words. Okay, so let's find the rate at which the average cost per t-shirt is changing when 400 shirts have been produced and sold. Now from looking at the graph right here, you can see that when X is 400, the average cost per shirt is barely changing. I mean, this line looks almost flat. Now, it does have a decreasing slope, but it is just changing so slowly. Yeah, it really, to the eyeball, looks flat. So it's going to be changing at a really, really slow rate, but it should still be decreasing. So what I want to find is the rate at which this is changing when x is 400. In other words, I want to find the derivative of 140 plus 13 root x all over x when x is 400. Okay, so first we need to find just the general derivative of 140 plus 13 root x all over x. And you can use the quotient rule to find that derivative, or you can, because there's only one term in the denominator, you can split this into two fractions and use the power rule, which is what I'm going to do. So I'm going to split this into 140 over x plus 13 root x over x. I have not yet differentiated, I'm just rewriting it. So 140 over x, I'm going to write as 140 x to the minus 1. And then here, how I do this is, well, there's a couple ways, but you could think of that term as in the denominator. You can think of this x as being root x times root x. The reason you do that is because two of them cancel. So you're left with 13 over the root x, or that's the same as 13 x to the negative 1/2. Okay, that looks easier to differentiate. So the derivative of 140 x to the minus 1, I'm going to bring the negative down, so it will be negative 140 x to the minus 2 plus, actually, no, it'll be minus a half times 13 is going to be minus 13 halves, x to the power of negative a half minus 1 is negative 3 halves. So that's the general derivative. Now I want to find that when x is 400. So the derivative of, rewrite it because I guess I could call it y or f, but let's rewrite it. The derivative of that when x is 400 is, plug 400 into that, so negative 140, you need a calculator here, times 400 to the minus 2, minus 13 halves, times 400 to the minus 3 halves. So approximate that on your calculator. So I've got negative 140. This means divided by 400 squared minus 13 over 2 times, I'm just going to enter this as 400 to the power of negative 3 halves. Okay, we'll get negative 0.0016875. Okay, so what does that mean? It's important that you understand what that means. Derivatives tell us the rate at which things change. So this is telling us that, so therefore, the average cost per shirt it's changing at this rate. Now we got a negative rate, so that tells us that the average cost per shirt is decreasing. That's what that negative means. So the average cost per shirt is decreasing at a rate of this much per shirt when 400 shirts have been produced. So, and this is a dollar amount, I mean it's average cost. So at a rate of, let's see, $0.00168875 per shirt when 400 shirts have been produced. Okay, what that really means is that if we produced one more, so the 401st shirt, the 401st shirt would actually cost this much less than the 400th shirt, roughly. Okay, it would cost, let's see, a fraction of a penny, but 0.0016875, that much less than the 400th shirt is what that really means. Okay, now suppose that the church finds that the revenue in dollars from the sale of X t-shirts is modeled by this function, revenue R of X equals 85 times the square root of X. So we're going to find the rate at which the average revenue per t-shirt is changing also when 400 shirts have been produced. So the average revenue per t-shirt is given by capital R of X over X. So we want to find the rate at which that is changing. So first we're going to find the derivative of capital R of X over X, which is 85 times the square root of X over X. Now you could, the hardest way here to do this would be to use the quotient rule at this step. It would really be a whole lot easier to simplify first. So I'm going to simplify. I just did that simplification. Where was it? Right here. Remember, I thought of the denominator as being root X times root X. So if we do the same thing, this actually simplifies to 85 over root X. And let's write it as 85 times X to the negative 1/2. And then use the power rule to differentiate that. So we'll get 85 times negative 1/2, negative 85 over 2, times X to the negative 3/2. That's the general derivative. So now we want to plug in 400. Okay, so we want the rate at which the average revenue per shirt is changing when 400 have been produced. So, right here, so negative 85 over 2 times 400 to the power of negative 3/2. Negative 85 over 2 times 400 to the power of negative 3/2. Okay, becomes negative 0.0053125. Negative 0.0053125. Okay, that's the rate at which the revenue is changing when 400 shirts have been produced. So revenue is actually decreasing at that point, which is kind of interesting. Revenue is decreasing as more shirts are made. So that, let's put some units on it, dollars per shirt, is the rate at which the average revenue per shirt is decreasing because it's negative when 400 have been sold, actually. In this case, X, when you're talking about revenue, X is the number of shirts that have been sold. So now we're going to use the information from the previous two problems to determine the rate at which the average profit per shirt is changing when 400 shirts have been produced and sold. Okay, so now we're going to put this all together. So the average profit per shirt. See, there's sort of a long way to work this and a short way to work it, but let's work through it the way I think that makes the most sense. So if C of X was equal to 140 plus 13 root X, and capital R of X we were given was 85 root x. Okay, profit is defined as revenue minus your cost. So it's defined as 85 root x minus 140 plus 13 root x. So let's simplify that. Distributing that negative, we get minus 140 minus 13 root x. So your profit P of x is the 85 minus 13 is going to be 72 root x minus 140. So that's our profit function. Tells us the profit from the production and sale of X shirts. So then average profit per shirt is given by P of X over X. So it would be 72 root X minus 140 all over X. And we're going to find the derivative of that. We find the derivative of P of X over X when X is 400. But first we're just going to find the general derivative, then we'll plug in 400. So we're going to find the derivative of this. Before we do, let's split it into two fractions. So we're going to do 72 root X over X minus 140 over X. Now this, as I've done before, simplifies to 72 over root X. So now if we rewrite both of those fractions with exponents so that we can use the power rule, we get 72 x to the negative a half minus 140 x to the minus 1. Okay, so now let's differentiate this. That's easier to do. So it's going to be the derivative of 72 x to the negative 1 half minus 140 x to the minus 1. So let's see, using the power rule, we've got 72 times negative 1 half x to the minus 3 halves. Negative a half minus 1 is minus 3 halves. When this negative 1 comes down and we multiply it times that negative 1, it's going to become positive 140 x to the minus 2. So we get, let's see, 72 over 2 is negative 36 x to the negative 3 halves plus 140 x to the minus 2. So that's the rate, that's the derivative of the average cost per shirt. Now let's plug in 400 to find the rate at which the average profit per shirt is changing when 400 have been produced and sold. And so we get negative 36 times 400 to the negative 3 halves plus 140 times 400 to the negative 2. And let's go approximate that on, on the calculator. So we have negative, let's try that again. Negative 36 times 400 to the power of negative 3 halves plus 140 times 400 to the negative 2. So I get negative 0.003625. Okay, now there was actually an easier way to work this last problem because we already know the rate at which the average cost per shirt is changing when X is 400 and the rate at which the average revenue per shirt is changing when X is 400. Because profit is defined by revenue minus cost, it also works that average profit per shirt is the same as average revenue per shirt minus your average cost per shirt. So, and then it's also true with the derivatives. So what we found was that the average what was it, the average cost per shirt was changing at this rate. Was it this rate? Yeah, this rate right here. So this is average cost per shirt, negative 0.0016875. So negative 0.0016875. That's the rate that average cost per shirt is changing. Rate at which, okay, I'm skipping steps. Rate at which the average cost per shirt is changing at x equals 400. Okay, so we do the average cost per shirt minus the average revenue we found right here was negative 0.0053125. Negative 0.0053. Where's my mouse? No. 0.0053125. That's, I'm just going to abbreviate here. I'm going to put revenue. That's the rate at which the average revenue per shirt is changing when x is 400. So if we go to the calculator and we subtract those two numbers, we've got negative 0.001685 minus negative or plus 0.00533125. We get 0.003625. Except I just realized because I got positive, I did this backwards. I should have done revenue minus cost, so I kind of did that wrong. I should have done, because profit generally equals revenue minus cost. So it should have been negative 0.00533125 minus negative 0.001685, and that does give me the negative, like I have right here, 0.003625. Okay.